we have the mining well itself, and then we have the cable and also the bucket. The cable weighs 2 pounds per feet, and then the bucket weighs 800 pounds, including the coal it carries. And our displacement is toward the top of the mining well, and then our acceleration due to gravity is working toward the center of the earth. And to do this problem, we have to divide the whole system into two parts, because when you pull 1 foot off the cable, we lose 2 pounds. Whereas when you pull this 1 foot, let's assume this bucket is 1 foot long. So when you pull this 1 foot, you lose 800 pounds. So it's not uniform. That's why we have to divide the whole system into two parts. For the cable from here to here, we'll do the integration for it's going to be our part A, and from here to here it's going to be our part B. And also in number 2 we have 3 sub questions. For the first one, we have to take for the cable, we have to take the integration from here to the middle of the mining well. And then for the second question, which is B, we have to take the integration from here to here. And also for the third one, we have to take the integration for the whole mine. In this video, we are going to be covering problem number 2. We are given with the density of the cable, and then the weight of the bucket, and then the length of the shaft. And we are to find how much work is required to pull the bucket to the midpoint, and then from the midpoint till the top of the shaft, also to pull the bucket all the way up the shaft. So here's our secondary picture, which is on the paper, and the length, and then the density of the cable, and then the weight of the bucket. So in part 2, what do we know? We know density of the cable is 2 pounds per feet, the mass of the bucket is 800 pounds, height of the mine well is 500 feet. By using these two information, we can derive the total weight of the cable, which is 500 times 2, and then we get 1,000 feet. And what we are looking for, we're looking for work done by lifting the bucket in 3 different situations, which is we already mentioned in our introduction. And then set up the general equation. So our general equation would be 3 of total work equal work done to pull the cable, work done to pull the bucket itself. So we're like splitting them so it's easier to work with. And then for work done to pull the cable is going to be point A. We're going to be taking the derivative of force, and then the limit is going to be point A till point B, and then dy. And then we broke down F into mg, since it's like we're pulling against gravity. So we also broke down m into 1,000 minus 2y, because every time you pull 1 foot, you lose 2 pounds. Meaning, if you were to pull 2 feet, so you times 2 by 2 equals to 4, so you lose 4 pounds off the 1,000 feet. If it were like 10, if you pull 10 feet, you times that by 2, it's going to be 20, so you're going to be losing 20 pounds off the 1,000 feet. So that's our general equation for WC. And then for WB, which is work done to pull the bucket, it's going to be mg. We did the same thing, we did it over here before. And so mg and dy, so that's our general equation for work done to pull a bucket. So we set up our 3 different situations over here to do the integration. For the first one, we set up our limits from 0 to 250, which is the halfway midpoint of the mine shaft. And then the G 1000, that's just the general equation. So we start from there. We take out the G, which is constant, and we left the equation over here, and then the second one we didn't do nothing, and then the third one what we did was we took the integration of constant, which is y, so we included a y, and then the limit, which is 0 to 250, and then minus 2, and then we took the integration of y, so we get y squared by 2, so we divide by, it's the anti-chain rule, and then from 0 to 250 is the limit, 250 is the limit, so, and then we're going to be leaving it like that for now, and then we're going to be working with this in later part. And for the bucket, what we did was we set up the limit, and then the m, the mass of the bucket itself, and then the weight, or actually acceleration due to gravity, and then the dy. And then the second one, we took the derivative of a constant, and we get 7,840 times by y. So we took the integration, and the limit is from 0 to 250. So we did the same thing for this equation, which is the difference. The only difference is the limit. So we set up the limits from 250 to 500, and then we did the same thing all the way through, and then we get this equation over here. So we're going to be working with this later, and then same thing over here. The only difference is the limit from 250 to 500, which is the maximum height, and we get y, and then we left it like this. So we're going to be working with this later on, and then in part C, same thing, except for the limit from 0 to 500, which is all the way up from the very bottom. And then we took the integration, and for part B, for WB, we did the same thing. And so in part 5, plug in particular information. So we took the general equation from part 4, and what we did was we plugged in the value of G, which is 9.8, and we plugged in the limits, which is 1,000 times 250, and then minus 1,000 times 0. And then this negative comes over here. We cancel out this 2 and 2, and then we plugged in the limits into y squared. So 250 squared minus 0 squared, and then we got this answer for our WC. And then for the WB, we did the same thing. We 7840 times y. We plug in the limit, and which is going to be 0. So we're ignoring this, and then we get the answer for this too, and then we get this foot-pounds in foot-pounds. And then in part B, pretty much the same thing. We just took the general equation over here, and then plug in 500 and 200, and then over here 500 squared minus 205 squared. So what we did was we cancel out this 2 and 2, and then we plug in 500 and 200, then the minus in over here, and then we get this answer, which is in foot-pound. So it's work done to pull this cable from midpoint to the maximum height. And then we did the WB also, from the limit is 250 from 500, same thing. And then in W and C, we set up the limit we already told, and plug in the limit values over here, and then we get this answer, which is in foot-pounds. And for WB, we did the same thing. We plug in the limit, and we get this answer. In part 6, give the answer. So we're going to be giving the answer. So to give the answer, we have W net equal WC plus WB. So we take the answer from part 5 for WC and then WB, and we add them together, and we get this answer in foot-pounds. And we did the same thing for B, did the same thing for C. And here's our answer. So to lift the bucket to the midpoint of the shaft, we need 3,797,500 foot-pounds work. And then for part B, to lift the bucket from the midpoint of the shaft to the top of the shaft, we need 257 to 500 foot-pounds work, and then to lift the bucket all the way up the shaft, we need 637,000 foot-pound of work.